Hey everybody, Mr. Longo is here to tell you a little bit about linear inequalities, and we're going to get into feasible regions and objective functions and all sorts of fun stuff. But before we do that, we have to talk about how you graph linear inequalities, especially a system of linear inequalities. So the first thing you're going to want to do is move these two functions into y equals mx plus b. It just kind of helps when you're working with inequalities. So this one would obviously just become y is greater than or equal to a negative 2/3 x plus 2. That should be something very simple to do. You're just getting y by itself. And then you're going to do the same thing for the second one. Now this one, I will say, when you divide by the negative, it will change the direction of your sign. So if you do that, you're going to end up with y is greater than 2x minus 7 after you get that one done. So what you're going to do is you're going to graph both lines and shade them. Now if you have different colors, it's going to work out really nice for you. So the first thing you want to do is graph this first inequality, y is greater than or equal to a negative 2/3 x plus 2. So there's our plus 2, there's our negative 2/3 slope. You do not have to continue doing all of the slope in both directions if you don't want to, but what really needs to happen is you make sure you graph your line and go across the whole graph. And we have to shade. So this says y is greater than or equal to negative 2/3. So when y is greater than a line, that's going to be above the line. Now you could also use a test point if you would like. If you would like to plug 0, 0 in and see if that's true or false. If you substitute 0, 0 in, we would get 0 plus 0 is greater than or equal to 6. That's false, so we would have shaded away from the test point anyway. And now we need to go work with the next example. So we have y is greater than 2x minus 7. So we're going to graph that. And we're going to go up 2 over 1, up 2 over 1. And remember, when you're graphing an inequality, that you need to have a dashed line if it's greater than or less than. It is only solid when it's greater than or equal to or less than or equal to. And now we need to shade again. So if we're going to shade this one, y is greater than, again, is going to be above the line. So we're going to shade above the green line. And only where you have overlap is where you have your final answer. Okay, so anything in this green area is considered the solution to this system of inequalities. Okay, and you know, you can put a little happy face over there so we know that that is our region. Now if you're just using a pencil, just make sure you darken the final area. Okay? So the next one is up for you to press pause and see if you can calculate or graph the system of inequalities, and click play when you're ready to see it and see if you got yours correct. Go ahead, give it a try. So the first thing, x is greater than 2. So again, inequalities. Greater than means we're going to have a dashed line. And since this is x is greater, when x is greater, we are shading to the right. Okay, so you should be just shading to the right of yours. Next step, y is less than or equal to 3. So remember, y is less than or equal to 3, solid line at y equals 3, which is a horizontal line. And then we need to shade below. We're going to need to shade below that one. Okay, so that's only 2 of our lines, so we still have more coming. The last one, again, you would probably want to manipulate this to y is greater than or equal to a negative x minus 4. So we're going to go to a negative 4, and we're going to go down at a rate of 1 over 1. And of course, you're going to go backwards, same way. This is a solid graph. And this is y is greater than or equal to, so we are going to be shading above this line. So again, we're going to shade above. And after you shade above and to the right of all of our different areas, you see that all three of those will fall into one shaded zone. And again, if you don't have highlighters, you're going to go in that little zone right there. So now we're going to ask some more questions. Is 5-1 a solution? So we go to 5-1. Is that in the double shaded region? Nope, it's not. What about -1-4? -1 up 4. Yes, it's in the green land, so that one is yes. Is 4-2? 1, 2, 3, 4 up 2. Is that point in the shaded region? Yes. Trick question. Is 2-3? Is 2-3? The answer is no, because it's on the intersection of a dashed line. If both of those were solid, the answer would be yes. But since it's on the intersection with a dashed line, the answer would actually be no. Okay? So that's graphing a system of inequalities. So now we're going to take it up a level. We're going to talk about finding maximums and minimums of a feasible region. Now, the feasible region is your shaded region. So on the left, it would be the green. On the right, it would be the pink. Maxes and minimums we're going to find based by substituting in our coordinates that make up the feasible region, and we're going to substitute them into this function, which is known as your objective function. Okay, that's our objective function. So the other thing you need to look at is a couple of different types of bounding. Since this has solution or a solid line, the region is closed. It will not escape that almost trapezoid looking type figure. When it cannot move outside and everything is closed up, that is called bounded. But in the pink example here to the right, it looks like it can continue forever and ever and ever in this direction, because these are arrows and there is no closing of the right side. So since it can continue forever, this one is known as unbounded. Okay, so let's talk about finding maxes and mins. To find a maximum, all you're going to do is substitute all four of these points that bound this feasible region into the objective function. So -1 times 3 is a -3, and 2 times 5 is 10, and -3 and 10 is 7. So you're just substituting the x and y into the objective function and figuring out what happens from there. So 2 times 3 is 6, 3 times 5 is going to give you 15, so 6 plus 15 is 21. -2 times x into the x and -1 into the y, so that's going to give you a -6 and a -1, so that will give you -11. And finally 6, 0 is going to give you 18 plus 0 would be 18. So the maximum is 21. It's the biggest value that occurs at the coordinate 2, 3. And your minimum is the smallest value. That would be -11, and that occurs at the coordinate -2, -1. Okay, so that's how you work with feasible regions, coming up with maxes and mins using the objective function. But what happens when you get to an unbounded? You're only going to have a max or a min. When it's bounded, you will have both a max and a min. But when it is unbounded, you're going to have a max or a min. You will not have both. I'll explain why. Let's go. So we're going to first find what we have. We have a bounded left side, so we have our coordinates. 0, 2, we're going to substitute that in. 0 plus 5 times 2 is 10. So we're going to have a 10 for that coordinate. And then we have 1, -1. So 1 plus -1 times 5 is a -5, so we're going to have a -4. Now the question of the day is 10 the maximum or is -4 the minimum? You cannot have both. So what you're going to want to do is pick a couple of test points. So a point that you know will fit in this zone. So let's say if we were to continue going that way and maybe we had a 10, 2. And if you still weren't sure, let's go even farther. Let's keep on going at that level and say, what if we got to 100, 2? Now again, these are test points. So substitute 10, 2 into here. We're going to have 10 plus 5 times 2 is going to give us 20. It's one of our test points. But that's kind of close to these, so let's go even farther. 100, 2. So 100 plus 5 times 2 is going to give us 110. So as you can see, the farther and farther away we get, the bigger it's going to be. So if it doesn't ever stop getting bigger, will you ever have a maximum? And the answer is no. So this would technically be our max. But what if we got to 1,000, 2, or 10,000, 2, or 1,000,000, 2? It's never going to have a maximum. So your test point tells you what you don't have. So you have a minimum of -4 at the coordinate 1, -1. All right, so that is an example of maximums and minimums with a feasible region and finding all of the coordinates, bounded, unbounded. So what are you going to do next? Tie the first two topics together. This is a real example of linear programming and using objective functions. So to do this, you have to first flawlessly graph the 3 constraints that are given. Then you have to find your intersections. Then you have to shade, find your feasible region, and then take all of your intersections that make up your feasible region and substitute them into the objective function to find your max and min. It sounds like a lot of work, but if you understood the first couple of questions, then you should be ready to go. So I would like you to pause this video and give this entire question a try on your own, and then click play when you're ready to see if you did it correctly. Give it a shot. So, first thing, x is greater than or equal to a -2. You should have a vertical line at x equals -2. Now for these, you especially want to be as accurate as you possibly can be. So straight edges and multiple points would be a great idea. Y is greater than or equal to a -1. So y is greater than or equal to a -1. And the reason why you want to be very accurate is because you want really accurate intersection points. Finally, we have y is less than or equal to a -x plus 4. So we're going to start at plus 4, and I'm actually going to plot points at a slope of -1 all the way until I find my intersections. It's very important that you have accurate intersections. Okay? And then, of course, we had our other intersection at the blue and the green line. And this would be our final graph that we need to have plotted. But notice I was very, very specific with my slope because we need the most important part is going to be our shaded feasible region and the intersections of that. So now we need to do a little bit of shading. So it doesn't get as messy. I'm not going to shade super dark like I did earlier. So x was greater than equal to the -2, so we're going to be shading to the right of the blue line. And y was greater than or equal to the -1, so I'm going to be shading above the green line, and then less than or equal to the purple line. So just so it's easier for you to see, we're to the right of the blue line, above the green line, and below the purple line. So I am just going to clean that up a little bit so you can see exactly where our region is. Our shaded region is just what's in this triangle. So it's important to know that that is a bounded feasible region. So we are going to be able to find both a max and a min. So we need our coordinates. You must test them all. So we have our intersection at 5, -1. You have another one at -2, -1. And you have your last one up here at -2, 6. So you need to plug all three of those into our objective function. So 5 times 2 is 10, minus a -3 is going to give us 13 for this guy. -2 times times 2 minus 3 times 6 is going to end up giving us a -4 and a -18, so it's going to give us a -22. And then finally we have a -2 and a -1, so 2 times a -2 minus 3 times a -1, that's a -4 and a +3, so that's a -1. So we have a maximum of 13 at the coordinate 5, -1, and we have a minimum of -22 at the coordinate -2, 6. All right, so that's how you put everything together. So before we get into the video on word problems, we need to just quickly discuss how you set up certain equations. Examples of less than or equal to, is no more than is another less than or equal to, and is at most less than or equal to. Greater than is a greater than symbol. Greater than or equal to gets the greater than or equal to symbol. But another way to say greater than is no more than. So no more than, or I'm sorry, no less than means it can't be any less than that number. So it has to be more than that number or equal to. Same with at least. At least that number means it's got to be more than that number or equal to it. So we're not going to do any solving on this word problem. We are just going to write the equations. So Dante is organizing help for a track meet. He needs at least 12 workers, timers, and t-shirt sellers. They make $20 an hour if they're timers, $10 an hour if they're a t-shirt seller. Warren can pay no more than $220 on the budget. So if T represents timers and S represents sellers, then we have timers plus sellers are going to work the event, and he needs at least 12 workers. So that has to be greater than or equal to 12 workers. Now the money aspect. The timers get paid $20 an hour, and the t-shirt sellers make $10 an hour. But we can only pay them a maximum of $220, so that has to be less than or equal to $220 in the budget. All right, so that is how you write your system of inequalities for this word problem. But we're not going to solve it. That's for another time. So this is Longo, and I'm out. See you, bye.